In discussion of thermodynamics of electrochemical cells, today I shall discuss type 3 electrodes and also queen hydrogen electrode. Every electrode reaction involves either oxidation or reduction processes. But by convention, this type 3 redox electrode refers to the reactions between reactions of a species between the two different oxidation states in solutions, and the one inert metal plate either platinum or gold have been inserted in these solutions. It is a very simplest type of this electrode, and we can represent this electrode as Mn1 plus and Mn2 plus. These are in solutions, and this inert electrode platinum is dipped into the solutions to carry out or to pick up this potential where it forms and supply where it is required. And this electrode I can represent this one, this cell, and here the platinum electrode is inserted, and this one contains the solutions Mn1 plus and Mn2 plus in solutions. This M is the metal and N1, N2 are the valencies, and this one is of higher oxidation state and this one is the lower oxidation state. And the reaction and the electrode reaction is a very simple. We can write this Mn1 plus N electron and giving this Mn2 plus and N1 minus N2 equal to N. This is the higher oxidation state, this is the lower oxidation state of this metal ion, and N, the difference of these two oxidation states, this N is the number of electrons involved in this process. So the potential of this electrode is given as E Mn1 plus Mn2 plus in solutions, and the platinum plate is equal to the standard potential, this Mn1 plus Mn2 plus, and here the platinum minus RT by NF and ln activity of this Mn2 plus and divided by activity of Mn1 plus. But these two ions remaining in the same solutions, and they are this ratio. We can take it by the ratio of these concentrations approximately. So this electrode, we can write this E naught Mn1 plus comma Mn2 plus, and within the solutions and platinum and minus RT by NF, and it is ln concentration of Mn2 plus divided by concentration of N1 plus. Approximately this activity ratio, we can take this concentration ratios, or at 25 degrees centigrade or at 298 Kelvin, this E equal to N1 plus N2 plus, and here is the platinum, and this one is the standard value, and E naught N1 plus N2 plus, and this platinum, and minus 0.059 by N, and here ln is converted into log of this N2, and here if I take this plus, then it will be 1, and N2 plus. And this one is the oxidized state. This is the oxidized species, and this one is the reduced species. So I can write this E equal N1 plus N2 plus, and here the platinum plate equal to E naught and N1 plus and N2 plus in solutions, and it is a platinum, and plus 0.059 by N and log oxidized species in general, oxidized species in this numerator, and here it is a reduced species in the denominator. So this is the general form of this expressions of this potential of this redox electrode, and these electrodes are of different forms, and this electrode, say it has different forms. One, I can take this systems containing metal ion of different oxidation state, different charges. And this one example, I can say this ferric, ferrous in solutions, and platinum. Or I can write this as ferric 4 plus, ferrous 3 plus, and platinum, etc. Stenic, stannous, etc. And these two systems containing anions. Here this containing cations, I can write containing cations of different charges, containing anions of different charges. This is the second form, different charges. An example, this FeCN whole 6 3 minus, ferricone, and another is a ferrocone, and this is dipped in this is in solutions, and platinum is inserted. This may also written as MnO4 minus and MnO4 2 minus, and here a platinum. Here the oxidation state is 7, here the oxidation state is 6, and 3 systems containing cation and anion together. This is also possible together. This one very popular, MnO4 minus and Mn2 plus and platinum. Or another example is Cr2O7 minus and Cr3 plus and this platinum. I set one example. One example of this redox type of electrodes is that ferric ferrous. This one is very simple and used in redox titrations also, and this one is Fe3 plus, Fe2 plus in solutions. Here the platinum. This is some sort of this picture of this electrode, and Fe3 plus, Fe2 plus solutions, and here it is a platinum. So this reactions of this electrode will be Fe3 plus electron and giving this Fe2 plus. This is oxidized species, and this is the reduced species, and the potential of this electrode. I can write this Fe3 plus, Fe2 plus, they are in solutions, and here the platinum equal to E naught, and standard value Fe3 plus, Fe2 plus, and here the platinum, and minus, or I can write a plus RT by F n equal to 1, and this Ln oxidized species, here the concentration of Fe3 plus, and the reduced species this one, and Fe2 plus this one. And this value actually could be obtained by coupling this electrode with a secondary standard electrode or this standard hydrogen electrode, and forming a cell, and the cell potential is obtained by the potentiometer. And at this value, at 298 Kelvin, this E naught value Fe3 plus, Fe2 plus, and here the platinum equal to 0.77 volt. So at 25 degrees centigrade, this potential is E, Fe3 plus, Fe2 plus, and this platinum equal to 0.77 volt and plus 0.059 and log, and this is the oxidized phase ferric 3 plus, and this concentration of a ferrous. This is the expressions of this potential, and this value could be obtained by using this by coupling with this secondaries or the standard hydrogen electrode, and the cell so formed is determined by means of potentiometer. On the basis of this formulation, one problem I can set which has been given in GATE 2014. This problem is a electrode is immersed in a solution containing 0.1 molar ferrous ion and 0.1 molar ferric ion is found to be 0.77 volt against a standard hydrogen electrode. Under standard conditions, and considering activity coefficient to be equal to unity, the potential of this electrode where concentration of the ferric ion is increased to 1 molar is and it is a gap to be found out. And this problem is this is the formula, and this one is given 0.77 according to this data, and this one written here plus 0.059 and ferric ion 0.1 molar and ferrous ion 0.1 molar, and this one log 1, this one 0, and so this is the standard value, and standard value is 0.77 volt. So when the ferric ion is increased to 1 molar, then the potential of this electrode equal to, this is the standard value given here, 0.059 log 10, this is 1 and this is 0.1, this is log 10 equal to 1, and the value comes up this one. So this gap will be, potential will be 0.83 volt. Now let us discuss the quinhydron electrode, and this quinhydron is a crystalline solid substance having 1:1 molecular compound joined by this hydrogen bonding. Whenever it is sparingly soluble in acid solutions, and when the dissolved quinhydron is dissociating into equimolar of quinone and hydroquinone. And this electrode is very simple to set up in this laboratory, and this electrode is widely used to determine the pH of these acid solutions. This electrode is very simple. Here the acid solutions, so where saturated with quinhydron, a pinch of quinhydron is required to saturate these acid solutions, and one inert electrode, say platinum is inserted into these solutions to pick up this potential and deliver when it is required. This electrode reaction is quinone plus 2H plus 2E and giving the hydroquinone, and this is the reduction reactions. So the potential of this electrode is E Q H2Q, or I can write this H plus and Q H2Q quinhydron in solid, and here the platinum equal to E naught, this hydrogen ion and Q, H2Q, it is in solid quinhydron, it is the quinhydron, and a platinum, and minus RT by twice F, 2 electrons involved. 2 electrons are involved, and so this is ln, and this activity of H2Q and divided by activity of this Q into 1 by activity of hydrogen plus square. But actually this quinhydron is slightly soluble in acid solutions, and they are present in equimolar mixtures of quinine and hydroquinone, and we are not going to draw this electricity from the cell, just these two are in equilibrium. So actually this activity of H2Q and divided by activity of Q may be taken to 1 approximately. So this value, and this value is a standard value, and this one is 0.6994, the standard value at 25 degrees centigrade, and this one we can write this minus 0.059, and here this ratio is equal to 1, and 2 will cancel, so it will give you this pH. So this is the formula, and in short we can write this one, this potential of this quinhydron electrode equal to this value, standard value, and minus 0.059 pH. So this one is, whenever this one is determined, pH could be obtained, and this one could be determined by constructing a cell coupling with a secondary standard electrode, just like saturated calomel electrode, and the cell setup will be like that. Cell setup, here the saturated calomel and the salt bridge, and here this acid solutions of unknown pH, and saturated with quinhydron, and here this platinum. So the cell so constructed, it is very simple. Here it is the acid solutions, here the acid solutions saturated with quinhydron, here the platinum plate is inserted, here this calomel, here this calomel, one calomel electrode is in a rough way. I can write this calomel. Here the platinum is fused, here it is blocked, and here this mercury liquid, and here this mercury plus mercurous chloride, and here this saturated potassium chloride. Here this lymph, and lymph is connected to this one. This one is the rough sketch. This is the positive electrode, and this is the negative electrode. Cell setup will be like that. The cell potential cell potential will be equal to E of right hand side electrode minus E of the saturated calomel. And this one, instead of this one, we can write here 0.6994 and minus 0.059 pH, and this value is standard value to 0.2415. So if we do this here, subtracting this one and this 9 and 7 and 7 and 5 and 4 0.1 and minus 0.059 pH. This one is determined by means of potentiometer. So this potentiometer determination of this cell potential gives this pH of these solutions, and this, as it is seen that as this pH is increased, E cell is decreased. So at a certain pH, the cell potential will be equal to 0. So this pH at which this cell potential equal to 0 will be 0.4579 divided by 0.059, and this one equal to 7.76. So above this pH, whenever this acid solutions will have this pH more than 7.76, this cell potential becomes negative, and whenever the cell potential becomes negative, the cell reaction becomes non-spontaneous. So in that case, the cell setup is to be reversed, means calomel, this quinhydron electrode to be placed in this anode, and this saturated calomel to be placed in this right hand side or this cathode. And this is the widely used electrode to determine this pH of these solutions. Actually, due to the different reasons, it has the setup of this electrode is very easy, and small amount of this solutions is required, and this reversibility is easily, very quickly attained. Not only that, unlike this hydrogen electrode, which is also popular to determine this pH of the solutions, here this oxygen need not be removed from this electrode cell, from this electrode. Not only that, any unsaturated compound or this heavy metal ions cannot affect this potential of this quinhydron electrode. Only the difficulty is that this solution must not contain any oxidizing or reducing agent. In that case, this quinone or hydroquinone will be attacked by this oxidizing and reducing agents. So there is also some disadvantages. Above this, whenever this solution is alkaline, means a pH is greater than 8, this electrode will not work. As in that case, this H2Q, this hydroquinone, this is the hydroquinone. Hydroquinone is the weak acid, and it in this alkaline solution begins to dissociate H2H plus and plus Q to minus. As in alkaline solutions, the hydrogen ion concentration is very low, and so this one is dissociating, and the linear relationship with this with this QH equal to 0.6994 minus 0.059 pH, this relation does not hold. Not only that, in this alkaline solution, so this pH is alkaline solutions, this hydroquinone is aerially oxidized. And another limitation I have already told, this oxidizing agent or reducing agent should not be present in the solutions. They will attack this hydroquinone. So this is all about the quinhydron electrode. In this context, I can cite one problem set in Tata Institute of Fundamental Research admission test for MSc 2014, and this problem is FAD is a redox active molecule which takes place in many important biological reactions. The redox potential of this FAD at pH 7 is given as this reaction FAD plus 2H plus 2E equal to FAD H2. This is the oxidized species, this is the reduced species, and the potential at pH 7 is minus 0.180 volt. Calculate the redox potential when this media is acidified to pH 0. And this FAD is very important compound in biological reactions, and it is flavin adenine dinucleotide. This solutions to this problem is that this potential of this one equal to standard potential minus RT by 2F ln, and this activity of this oxidized species, reduced species divided by oxidized species, and into 1 by activity of hydrogen ion square. This one equal to keeping this one in one place and minus 0.059 pH. When this bracketed term, this one is minus 0.180 given, and this is the bracket, this term within this one, and this pH equal to 7 and 7 multiplied, and when pH 7, this potential is minus 0.180. So this term within this bracket is equal to this value minus 0.180 plus this one in left hand side, so plus 0.059 into 7 equal to 0.2334. And from this equation it is very clear that whenever this pH equal to 0, this term will vanish, and this potential of this electrode will be the term within this bracket, and this term within the bracket is 0.233 volt. So this is the answer. So thanks to you all who are watching this. So this is all about this thermodynamics of electrochemical cells and type 3 redox electrodes and quinhydron electrode. And this next class I shall discuss this glass electrode. This is also very important electrode to determine this pH of this solution. Thanks to you all who are watching this video, and if you like, then please subscribe.